So in my next presentation, I would like to talk about the pipeline processor design. Okay, so the outline of this presentation is shown here. So I'll talk about the pipeline, data path and control in details. I'll talk about the pipeline hazards. What do I mean by a hazard? I'll talk about this later. I'll talk about data hazards and how we can implement forwarding. I'll talk about how we store the pipeline, the control hazards, and I'll talk a little bit about the delayed branching and dynamic branch prediction. So all of these are topics of this presentation. Let us just recall the single cycle data path. Okay, so this is actually single cycle data path. So notice that we can break it down into 5 stages. Notice that we have here the instruction fetch. So we fetch the instruction from the instruction memory, and the instruction will be available at the output of the instruction memory. During the second stage, we decode the instruction. Notice that there is a control logic, which is not really shown here. This is the main control. At the same time, we read from the register file. At the same time, we can also do the address calculation. This will be for the branch target address. Sorry, this is for the branch target address. We can actually use an adder here. Okay, even during the same stage, we can actually use an adder here to calculate the branch target address. In the third stage, it's called execute. I'm using just an ALU, okay, for executing the instruction. We produce the ALU result. Now, in the fourth stage, we can use it to access the data memory, okay, for load and for store. And in the last stage, which is called the write back stage, nothing is shown here at the end, but really it's the same register file that appears here at the end. And you are writing to the register file. So you can think about the register file itself. So notice this looping here going back into the register file. So think about the register file, okay, replicated here. Okay, it's not replicated, it's just the same register file. But basically, this write back stage is also writing to the register file, the same resource in the hardware. Right. In the case of the single cycle CPU, we were doing all of this in one cycle. Recall that, okay, in the case of the single cycle data path. So the question is now, I would like to improve the performance of this data path. So the question is, how to pipeline the single cycle data path? So how do I convert this from single cycle to a pipeline CPU? Yes, Khalid?
We just add registers.
Exactly, as we have seen in the case of the synchronous pipeline, yes. So what we need to do is that we need to introduce pipeline registers at the end of each stage, but we have to do it carefully. Okay, we have to do it carefully. So now the answer is to introduce pipeline registers at the end of each stage. So now we are going to introduce pipeline. This becomes actually now a pipeline data path. Now we add registers as much as needed. Okay, yeah, for example, after fetching an instruction from the instruction memory, we need to have an instruction register here. So that's my instruction register. After incrementing the PC, that will be my next PC, NPC. I need also to have a pipeline register. Notice that after reading 2 values from the register file, this is bus A, this is bus B, these were wires. So now we have to put them inside registers. So this is A and B. These are 32-bit values. So these are 32-bit registers. After extending the 16-bit immediate, I can use an immediate register. After calculating the branch target address, I can use a branch target address register. Okay, so this is BTA, branch target address here register. After calculating the ALU result, I need here a result register. Okay, the value here of B can be copied here to D. This is actually my data input to the data memory. After actually selecting the ALU result or the data at the output of data memory, we can place it in a data register before we write it back into the register file. So all of these are now pipeline registers. These are internal registers inside the pipeline data path. So we are actually introducing all of these registers inside the data path to make it pipeline. Okay. Now notice that all of these registers are connected to the same clock. The same clock. The clock is connected to all of them. Okay, that's actually here I'm going to highlight the clock. That's my clock, which is connected to the clock input of all of these registers. So all of them are changing. So now we have many registers inside the pipeline data path, and all of them are changing at the same edge of the clock. So we can have many registers in the pipeline as needed. So for example, after the instruction memory, after we fetch an instruction, we have to store the instruction in a register. So this is my instruction register that appears at the output of the instruction memory. If I would like to increment the PC, this will be my next PC register. If I would like to calculate the branch target address, I need an adder. So this is my branch target address register. Also, when I read two registers from the register file, RS and RT, I will have their values on bus A and bus B. But before I start executing, I need to store the data in my registers A and B. So these are two registers. Also, when I extend the immediate, I need a register for the immediate before I start executing it, before I use it in the ALU. When I execute the instruction in the ALU, I need to save the result of the ALU. So I need a register. Notice that this is R, which is the ALU result. The same thing, if I would like to store data inside the data memory, I need to copy it, okay, from the B register to the D register. So I need also a D register at the input of this data memory. Also, before we write back, we need the data that should be written back at the output of this multiplexer. So all of these are registers that have been introduced in the pipeline, and all of them are connected to the same clock signal. So all of them will change at the same edge of the clock. Now, notice that although this is a pipeline data path, there is a problem with this pipeline data path. So this pipeline data path has a problem. Can you tell me what is the problem with this pipeline data path? There is a small problem with this pipeline data path. In fact, it's not really small. It's actually a big problem. Okay, it's not correct, and it does not really work properly. And there's a reason for that. Can you tell me why? What is the problem in this data path and how we can fix it? Anyone? Type. So yes, Mustafa.
Maybe when you add the second the PC, you need to add 4.
That's basically adding 4. So this is +1, it's just adding 4 because we are adding to the upper bits of the PC. The least significant 2 bits are 0, 0. That's not really the problem. So we're adding 4 because this one means 1, 0, 0 in binary. It's actually 4. But I can just use an incrementer here and add to the upper bits of the PC. That's the same thing as adding 4. So this does not change anything. Now, let me explain to you this problem. So you can see that here the clock is ticking. So there is a problem with the register destination. Here is the problem. So the problem is shown here, okay, in this multiplexer, in this register destination RW. And it is caused by this multiplexer. So this is actually my problem here, okay? Now, why is it a problem? Why is it a problem? Anyone?
Can you repeat the question, Doctor? I mean,
now, okay, so you see the question here is I'm saying that there is a problem with the register destination. So after we have pipelined the data path and introduced the pipeline registers, so now the instruction is going to go through these 5 stages of the pipeline. So we have 5 stages. I talked about them previously: the instruction fetch stage, instruction decode, execute, memory, and write back. So basically the write back, we only have data, and we need to write back this data into the register file. So I'm saying that this multiplexer here that is going to produce the destination register, so we can select RT or RD, as we have done in the case of the single cycle. So we can select actually which register to write in the case of the pipeline processor. However, because of pipelining, okay, the way that it is now in the data path is going to create a problem.
I think the write back will change when we introduce a new step So if the data, writing back data to bus W, will it change after a few steps? I mean, we should consider that the last step should write to the corresponding destination, register destination, and this will change immediately after we know the new opcode. So we should not change until we finish the data, until we finish writing. I think so.
Right. Let me try to see if I understand your question. Let me probably explain it slightly differently. So the instruction which is here in the instruction register, is it the same as the instruction which is in the write back stage? So that has this data. So after we have calculated the data and the data exists here and would like to write it back, is it actually writing back the data of the instruction which is here in the instruction register, or these actually are two different instructions?
Different instruction, because it's changing.
Yes. So these are two different instructions. Why? Because remember that we are fetching an instruction every cycle. So because of pipelining, we are fetching an instruction every cycle, even before the instruction which is in the write back stage has completed. So the instruction will complete after writing back its data into the register file, and then it's going to complete. So by the time the instruction has reached the fifth stage, already we have many instructions in the pipeline. And the instruction which is in this instruction register is different from the one which is in the write back stage. So for this reason, this instruction which is in the write back stage will probably write to a different destination register than the one which is in the in the second stage. So these are two different instructions, and because of this, the one which is in the write back stage is not really writing back to its destination register. It's writing to some other instruction destination register. Okay, so that's really the problem. So by not being careful in the design of the data path, we might actually encounter this problem. So the instruction here in the instruction decode stage, which I just highlighted, is different from the one which is in the write back stage, because we have now multiple instructions in the pipeline at the same time. That's really pipelining, is a form of parallelism. So we have to take into account pipelining. And because we have now multiple instructions in the pipeline at the same time, so the one which is in the write back stage is trying to write back its result to the destination of another instruction, which is in the second stage, okay, which is in the decode stage. So the instruction here, which is shown in the instruction register, okay, its output now it is in the decode stage after we have fetched it, okay, so it's now in the decode stage. Whereas the data, okay, this is the result of a previous instruction that is now has reached the write back stage. Okay, so because of this, this is going to create a problem. How do we resolve this problem? So this is not a correct data path. We have to fix it. How do I fix it?
Can we move the multiplexer to the last step? So to determine when to write at the last step instead of.
Well, yeah, but that's not really. We don't really want to do it this way. This actually does not really solve the problem completely, because still we have to, and well, we have multiple instructions, right? We can do that like you are saying, but this is not really a complete solution. Let me explain it, okay, how we can do it. So now, yeah, how do we solve this?
Maybe we can add another register.
Yes, it's about actually just adding registers, pipeline registers. So what we have to do is that, let me show to you how we can solve this problem. So this multiplexer here, this multiplexer is very important. We don't really want to change it. We just need, actually we need it because we need to select RT or RD as my destination. But we do this while the instruction is here in the second stage of the pipeline. So after we have fetched it, we save the instruction inside this instruction register. During the next cycle, this will be the instruction decode stage. Okay, we decode the instruction. I need to show you the control signals, but I will do that later. So we check the opcode, and then based on the opcode, we can generate this control signal register destination that is going to select whether RT or RD is my destination. But when I actually select it, I need to save it. I did not save it before. So I need to introduce now a pipeline register, which is RD2. Okay, so RD2 now will contain the destination, which is either RT or RD. So this will be just a 5-bit register because my registers here are only 5-bit numbers. So I need to save the destination in RD2. So this will be done. So this RD2 will be connected to the same clock cycle. So therefore, okay, we save the destination register in RD2. So all what we need to do is that we need to introduce a pipeline register. And then next cycle, we propagate RD2 to RD3 when the instruction moves into the next. So every time the instruction goes to another stage, so we copy the value of the destination register. So it goes from RD2 to RD3, and then from RD3 to RD4. And now in the write back stage, I have the data and I have the destination register. So notice that RD4 is connected now to RW. And we have now the data is connected to bus W. And therefore, we do the write back during the last stage of the pipeline. So it's very important to save the destination register. And for this reason, we have to introduce pipeline registers for the destination. That's how we fix it. Otherwise, it will not work. So because we have here RD2, RD3, RD4, so these can save the destination registers of the instructions, which are in the, so after we have produced it here, okay, by the multiplexer for this register destination. So this multiplexer is going to produce it. And this is my control signal. Then we save it in RD2, then we propagate it to RD3, then we propagate it to RD4. So as the instruction is moving from one stage to another stage, its destination is moving. And we have different destinations in RD2, RD3, RD4 for the instructions which are in the execute stage, in the memory stage, and for the write back stage. So these can be different instructions with different destination registers. So you have to understand pipelining, you have to understand the parallelism, okay, in the pipeline. All right, so you can see that how it's propagating over time. And then during the write back stage, we have both the data and the destination, and we write back the result into the register file. Okay. Now, graphically, really, we need to understand pipelining, and we would like to see what's really happening over time. So now we have multiple instruction execution over multiple clock cycles. Okay, and the instructions here are shown in a program order. Let me just go back here to, okay, so notice that the instruction here are shown in a program order, and this is time, which is shown in clock cycles. So I really would like to show to you, okay, what's really happening cycle by cycle in the pipeline. So suppose I have a load word instruction. So the first step is to fetch the instruction from the instruction memory. So I am here. So this I am here is my instruction memory, and this pipeline register is nothing but the program counter. So we need the address, okay, to fetch the instruction. And then during the next clock cycle, the output of the instruction memory will be the instruction register. And of course, we can actually also have other pipeline registers here, for example, the next PC and so on. So once we have the instruction, we can actually read two registers from the register file. So this is my register file. So during clock cycle number 2, we are reading, okay, here, for example, we have S5. Okay, it's my source register. And at the same time, this add instruction here is being fetched from the instruction memory. So two things are happening in the pipeline during the same clock cycle. That's very important to understand. Okay, because of pipelining, we have now two instructions now are in the pipeline. One is being fetched, one is in the second stage of the pipeline, which is the instruction decode stage. So it's reading the value of S5, okay, from the register file. And at the same time, we have the add instruction, which is being fetched from the instruction memory. At clock cycle number 3, the load instruction has reached the execute stage. So we use the execute stage for address calculation. In this case, we have to add the value of S5 plus 8. Now notice that here from the register file, you can read up to 2 registers, but in the case of the load, we only need 1, that's fine. Okay, but some instructions would require 2. So for this reason, Okay, this is, I'm showing here, let's say this is the pipeline register. This is a graphical representation. It's just a small representation for the pipeline. So at clock cycle number 3, the load instruction has reached, okay, the ALU. So now it's using the ALU for address calculation. The add instruction is being decoded in the second stage. It needs to read S2 and S3, okay, from the register file. And at the same time, the OR immediate is being fetched from the instruction memory. So 3 things are happening in the pipeline during the same clock cycle. That's what you need to understand. You need to understand that now we have multiple instructions in the pipeline during the same clock cycle. At the clock cycle number 4, the load instruction has reached the data memory. Okay, that's clock cycle number 4. So now the load instruction is reading the data from the data memory. At the same time, the add instruction is executed in the ALU. At the same time, the OR immediate has reached the second stage of the pipeline. So it's reading T3 from the register file. At the same time, we're using the second stage to decode the instruction and to generate the control signals. At the same time, during clock cycle number 4, also the subtract instruction is being fetched from the instruction memory. So 4 things are happening at the same time. And because we have 5 stages in the pipeline, during clock cycle number 5, okay, notice that the load word is writing back the data into the register file. Now the add instruction has reached the memory stage, data memory, but really the add instruction does not really need to load or store anything. So basically it's going to bypass. So the ALU result is going to bypass without doing anything. So we have a bypass here, okay, for the data memory. The OR immediate is being executed. The subtract instruction is reading 2 registers from the register file S2 and T3. And the store word instruction is being fetched from the instruction memory. So that's basically 5 instructions in the pipeline at the same time, okay, because we have 5 stages. So keep this figure in mind, because that actually shows you what is really happening cycle by cycle, okay, inside the pipeline. And then we can continue like this, okay? Now, of course, we'll have more instructions in the program. We can continue down here according to the program execution order. So these are the instructions. Of course, the last instruction is not really a store word. We'll actually have more instructions that we have to fetch, decode, execute, and maybe sometimes to access the data memory and then write back. So we have these 5 stages in the pipeline, and every instruction has to go through these 5 stages of the pipeline. Okay.
It should be continuum 5 stages.
So we can actually have millions or billions of these instructions, and therefore this graph, okay, this graphical representation of the pipeline will continue. It's going to go down. But the important thing is that to realize that you can actually have 5 instructions in the pipeline. 1 is currently being fetched. Let us take a look at clock cycle number 5 again. This clearly shows 5 instructions in the pipeline. 1 is being fetched. 1 is in the decode stage. Okay, so while the store instruction here, so while this store word is still being fetched from the instruction memory, so that's the instruction memory here, right? The subtract instruction is being decoded, and also it's okay, accessing T2 and T3. Okay, so it's in the second stage. The OR immediate is being executed by the ALU. Okay, the add instruction has reached the data memory, but really it does not really need this memory stage, but it's going to bypass it. But it is now in the 4th stage of the pipeline. And finally, the load instruction is in the last stage, in the 5th stage, which is the write back stage. So it's writing the data back into the destination, which is T6. T6 is the destination for the load word instruction. So that's actually is a graphical representation. Yes, Abdulrahman?
If the add instruction needs the register from load instruction, what will happen?
Now actually it's the interesting part of pipelining. So when we have data dependencies, what will happen? Okay, what will happen? This is actually a good observation, Abdulrahman. I'm going to actually answer this later. Okay, so give me some time. Okay, just to explain the idea of the concept of pipelining, and then we look at when we have dependencies between instructions, these will cause problems for the pipeline. And because we have this kind of overlapping, okay, because we have multiple instructions in the pipeline at the same time, we have to take into account, okay, these data dependencies. So here, I did not really have any data dependence, just to simplify the idea, but I'll come back to your question later, okay? I'll come back. I don't really want actually to jump into the answer of this question, because this is going to take me actually a full lecture just to explain to you what will happen, okay, Abdurrahman? Right. So, so let us proceed. Now, what we have done here, I just show here the instruction memory, registers, ALU, data memory, and register file. I can do it slightly differently, okay, using this diagram. So notice that here cycle by cycle. So here I have, let us say, a different sequence of instructions: load word followed by another load word followed by or immediate, subtract, and store. So notice that cycle by cycle, what's really happening. Now, notice that some instructions like load will require 5 stages. Okay, every instruction has to be fetched. So this is IF, the instruction fetch stage. ID means the instruction decode stage. In the instruction decode, okay, we decode the instruction to generate the control signals, but at the same time, we read the registers from the register file. So we read the value of the registers from the register file. During the execute, we execute the instruction, but for load and for store, we use the execute stage for address calculation. Memory is needed, okay, by a load instruction, and then we write back. The same thing for the second load, okay, but notice that how, okay, pipelining is working. Okay, so we start fetching the second load during the clock cycle number 2. So while we are fetching the second load, okay, in clock cycle number 2, the first load is already in the decode stage. Okay. Now, while we are fetching the or immediate at clock cycle number 3, already I have the previous load, okay, in the decode stage, and the second previous load is now in the execute stage, and so on. Now, notice that some instructions don't require the memory stage, so they will simply bypass, like, for example, or immediate, subtract. They don't really need the memory stage, whereas load will require the memory stage because it has to read from the data memory. Here also store requires the data memory stage. Notice that store does not require write back. So basically it's going to bypass the write back without writing back anything. All what we need to do is just to disable the writing of the register file. So even though the store word has reached the write back, it will do nothing in the write back. It will not really modify any register in the register file because the store does not write to the register file. The store writes to the data memory. So after doing the data memory, the instruction will be in the during clock cycle number 9. The store will reach the write back, but it will do nothing in the write back stage. So as clearly indicated that some instructions are going to skip some stages without doing anything. Also, you can see that we can have up to 5 instructions can be in the pipeline during the same cycle. Okay, why we can have 5 instructions in the pipeline? Because we have 5 independent stages in the pipeline. Now, pipelining, because we are introducing registers at the output of each pipeline stage, we have many pipeline registers. Okay, so this is really to save the data, okay, or the instruction, let us say. At the output of the first stage, okay, the instruction fetch, we save the instruction. But at the output of the second stage, we save the data from the register file. At the output of the third stage, we save the ALU result, and so on. Okay. So, so because we have here these pipeline registers and we are saving, okay, what the instruction needs, okay, from one stage to another stage, we can actually have multiple instructions in the pipeline at the same time. So this is a form of instruction level parallelism, which is called ILP. ILP here means instruction level parallelism, and we have it in the pipeline. What about the control signals? So this is my data path. Now I need to make it complete. I need to add the control signals. So after we have fetched the instruction and the instruction exists here in the instruction register, maybe I need actually to use my pen tool again. So this is actually where my instruction is. So we save the instruction inside this instruction register. What will happen to the control signals? Well, the output of this register is the instruction itself. And we have the 6 bits here. okay, 6 bits. So we have actually the output of this register consists of 32 bits because the instruction is 32 bits. And we have 6 bits are for the opcode. So we need actually here, okay, to decode the instruction and generate the control signals. So notice that we have many control signals here: register destination, register write, ALU source, ALU up. I also have memory read, memory write, write back data. So these are main control signals. Also, I have for this extender, this is for zero or sign extension. I also have PC source. Okay, this is actually for controlling the multiplex input. So all of these are control signals that we need to generate properly for each instruction. Now we are going to use exactly the same control signals, the same control signals that we have seen in the case of the single cycle data path. We are going to use them in the pipeline data path. So there is nothing changed here. Okay, but there is a small difference that I'll talk about. Okay, but in terms of the control signals, they are exactly the same control signals that we have seen in the case of the single cycle data path. So there is no need to change the control signals, but there is something else that needs to be changed. Okay, so what needs? Yes,
Doctor, I'm assuming we use registers as well.
Now, this is actually the big difference, is that although we are using the same control signals, but what should we do to these control signals as the instruction moves from one stage to another stage?
Save them in registers.
Exactly, we have to save them. So we have to introduce pipeline registers for the control signals as well. So this is something which is very important. So now we have pipeline control. Okay. So this is the main control. So we need the opcode. And I'm going to use also the function code. I'm going to combine here the main and the ALU control. You can just actually use the one logic for both. Okay, so the main control is going to produce, the main here is going to produce all the main control signals. And the ALU control is going to produce only the ALU control for the ALU only, just for the ALU. Okay, to control the ALU. So this will be the, so for this reason, for the ALU control, I need also the function in addition to the opcode. Right, so we are going to produce all the control signals, but not all of them are needed during this second stage of the pipeline. Only register destination and the extender op are used here. The extender op is shown here, are used in the second stage, the instruction decode stage of the pipeline. So use the register destination to select whether RT or RD is my destination. The output of this multiplexer will be saved in RD2. Now, the remaining control signals are going to be needed in the later stages because we still have execute, we have memory access, and we have write back. Now, the instruction is not really yet in these pipeline stages. So for this reason, we have to wait until the next clock cycles actually to start using these control signals. So I'm going to here to add a pipeline register to save these control signals because they are not going to be needed now during this clock cycle. I'm going to need them in later clock cycles. So for this reason, we save. So this is why we have to use additional registers in the pipeline to save the control signals. This is the big difference between the single cycle and the pipeline. In the case of the single cycle, we did not really use any registers. But here, because we have a pipeline that consists of 5 stages, we have to use registers, okay, at the output of each stage. Now, during the next clock cycle, the instruction will reach the execute stage. Okay, so we use some of these control signals from the output of this register. So notice that all of these registers are connected to the same clock. So every time we introduce, okay, a pipeline register, we have to connect to the same clock because everything is synchronized with the same clock signal. Right. So we use the output of these pipeline registers. So we use the output of this register. So I call it here the execute, means for the execute stage. So we have ALU source is going to control the multiplexer at the second input of the ALU. And I have the ALU up. This is for the ALU control. This is why I combine here the main and the ALU control to generate all the control signals during the second stage of the pipeline. So use the ALU up to execute the instruction on the ALU. Now, some control signals will be needed later, so we save them in another pipeline register. This is for the memory stage. Notice that here I have another register. Again, it's connected to the same clock, but we're not going to use them now during the execute stage, so we save them for the memory stage. Okay, now notice that before I reach the memory stage, I need the execute stage here for the jump and for the branch control. Because I have PC control, because I have this PC source, I have to control this multiplexer. Now, in the case of the ALU is going to be used for branching. In the case of you have a branch instruction, we are going to execute the branch on the ALU. We just do a subtraction, we just compare. And then the output can be either equal or not equal. So I call it the zero flag. The zero flag will indicate if they actually are equal or not. I use the zero flag here for branching. But I also have here control signals for a branch and for a jump. This is based directly on the opcode. So if you have a branch, we have to check the zero flag. If you have a jump, the jump is always taken, and we change the PC source accordingly. Right. So now for the memory stage, we need memory read, memory write, and write back. Okay, so we're going to use these during the next cycle, during the memory access stage. Okay, in the case of load, we use memory read. In the case of store, we use memory write. And we have this write back data that's going to control the multiplexer. Either we select the ALU source or we select the data at the output of the data memory. So that's the importance of this multiplexer. We still need one more control signal. So we are going to save it in this write back for the write back stage, which is whether we enable or disable the writing of the register file. So this is my register write control signal. So notice that we delayed the register write until the write back stage. So notice how we saved it. So register write was produced by the main control, but it was propagated, okay, in the pipeline until we reach the last stage, which is the write back stage, and then we use it to write back to the register. So this is why we have to have a careful implementation for these pipelined for these control signals. So they have to be pipelined, and therefore we pipeline the control signals just like data. So as the instruction goes from one stage to another stage, some data are going to be propagated, okay, from one stage to another stage, but also we have to save and we have to pipeline the control signals of the instruction, because the control signals, okay, will tell the instruction what to do. Okay, so these are the control signals. We don't really need actually to pipeline the entire instruction, because already we have decoded the instruction during the second stage of the pipeline. So there is no need actually to propagate the complete instruction. So the control signals are sufficient, okay, to tell, okay, what is supposed to be done at every stage of the pipeline. Any question about this? So this is called pipeline control. So now we have a complete data path, and also we have a pipeline data path and pipeline control. Right. So this is a summary of pipeline control. We are going to use the second stage, which is the instruction decode stage. So during the instruction decode stage, we generate all the control signals. So produce all of them. You don't really have to produce some of them and then later, no, just produce all of them. And then what you have to do is that you have to introduce pipeline registers just for the control signals. So we're going to pipeline the control signals as the instruction moves, okay, from one stage to another stage, we pipeline the control signals. And therefore, we are going to extend, okay, the pipeline registers to include the control signals. So this means that the control signals are going to indicate what the instruction is supposed to do at every stage in the pipeline. Now, the instruction itself is no longer needed, as I explained, okay, in the previous slide. Just the control signals will tell what the instruction is supposed to do at every stage in the pipeline. So now we look at each stage and we see, okay, what are the control signals which are needed in that stage? Okay, so in the case of the second stage, we generate all the control signals. So the control signals are generated, but we need only register destination and the extender up. So these are used in the second stage. Also, we can use the jump, which is used for PC control. So we can jump early in the pipeline. Now, in the case of the execute stage, we need ALU source, we need ALU up, we need the branch. Okay, so these are needed in the execute stage. Also, the ALU is going to generate a 0 signal, which is used to control the PC in the case of branching. In the case of memory stage, we have memory read, memory write, and write back data. And in the case of the write back stage, we only need one control signal, which is the register write control signal. This is used in the last stage of the pipeline. Right, so this is a summary of the control signals. These are exactly the same control signals that we have seen, okay, before. Okay, so I'm showing here the decode stage. I'm showing here the execute stage. Okay, these are the same control signals that we have used in the case of the single cycle, but we are now using them in the case of the pipeline data path. Okay, this is for the memory stage, and this is the write back stage, and this is PC control. So I'm showing actually a more complete table. So notice that in the decode stage, we use only register destination and the extender up. So in the case of R type, the destination is RD. In the case of the immediate type, add immediate, set less than immediate, and so on, we use RT. So this is my destination. And for some instructions like store and the branch and the jump, notice that I don't really care. Why? Because I'm going to disable the writing of the register file. So notice that here we enable. So in the case of register write, okay, I'm jumping here to the last stage, which is the write back stage. We enable the writing. Okay, for all of these ALU instructions, we enable the writing, including the load, but we disable the writing in the case of store, in the case of a branch, and in the case of a jump, we have to have register write equal to 0. In the case of memory stage, so before that, in the case of the extender up, it means that either we have sign extension or we have 0 extension. And sometimes we don't really care, like in the case of the R type, because there is no immediate, there is no need to extend. And so that's the extender, okay? In the case of ALU source, either we can actually select here input 0, which means that the value of register RT, this should be my second ALU source, or 1, it means the immediate, okay? And sometimes in the case of a jump, we don't really care because there is no execution. The ALU operation, this is going to be the operation that's going to be used by the ALU. We use the function code in the case of R type. In the case of add immediate, we do addition. In the case of set less than immediate, we do set less than. So this is the operation that should be done by the ALU. Notice that in the case of load and store, load word and store word, we just do addition. Add and add. Because we use the ALU for address calculation. So we do addition. In the case of branching, branch if equal, branch not equal, we do subtraction. Why? Because we need to compare. So we use subtraction to compare, okay, the values of two registers. Notice that ALU source equal to 0 in the case of branch, because we have to have both RS and RT as inputs to the ALU. So my second ALU input is the value of register RT. So we read it from the register file. In the case of memory read and memory write, memory read will be equal to 1 only in one case, in the case of load. Memory write will be equal to 1 in the case of store. And in the case of write back data, it is 1 in the case of load word, otherwise it is 0. Now notice that sometimes we don't really care, like in the case of store, branch, and the jump, because really the instruction does not write anything into the register file. Right, so these are the control signals, okay? So these are the control signals which are identical to the control signals that we have seen in the case of the single cycle, but I'm showing it actually stage by stage. Okay? In the case of branching, now notice that in the case of branching for PC control, this is PC control, I forgot to mention this. Now notice that it is next PC. If you are not really jumping or branching, it is just next PC. In the case of jump, we use the jump target. We have to select the jump target. So this PC control is used actually for the multiplexer at the input of the PC. So 0 means that do not jump, do not branch, just actually go to the next address in memory. That's the next PC. In the case of a jump, we select input 1. That will be the jump target address. In the case of a branch, it's interesting. It can be 0 or 2. Now 0 means that we did not branch. 2 means that we we went to the branch target address. So T2 here means that the branch target address. So this all depends whether the branch is taken or not taken. If it's not taken, we select input 0. If it is taken, we select input 2. So remember this in the case of the branch instruction. Okay.
I have a question.
Yes.
At every clock cycle, we take then we start with a new instruction. But in the case of branching, for example, sometimes we branch, but we need to read registers also. So
jump and branch actually create a small problem for the pipeline. So because they are delayed. So by the time actually we have executed the branch, we have actually 2 instructions in the first 2 stages of the pipeline. I'm going to postpone my coverage of jump and the branch to a later lecture because I need to go into the details of. So they will have a certain hazard. So jump and the branch are always cause problems actually for pipelining. So I need to talk about the control hazards, which are introduced by the jump and the branch. So let us actually keep it till another lecture. Okay. The problem is that they are delayed. So by the time you have executed the branch, okay, you already have 2 instructions in the first 2 stages of the pipeline. So by the time you have actually branched, already we have the next 2. So if the branch is not taken, that's okay. But if the branch is taken, you have to get rid of these 2 instructions that are in the first 2 stages of the pipeline. Do you understand this problem?
Yes. That's
now,
what I mean.
This problem will be explained in more details in a later lecture. Okay, I'll come back to this in great details.